Hello, in this set of notes we're going to be briefly discussing the importance of significant figures in chemistry. Significant figures is something that you likely haven't encountered before in your scientific career, but it's something that's really important to the way that we do math and science. And in chemistry, it's the year that we usually take to really practice our skills with significant figures. So as we go through this year, it's going to be really important that you're good at this. It's going to keep coming up all through the year, so it's important that you master the skill early, and if you have any questions on any of this, make sure you stop in and ask. So the first thing here to talk about is that there are two general kinds of numbers. There are exact numbers and approximate numbers. In math, everything is exact. All right? We talk about things where we're counting, or mathematicians have these perfect ideas of these perfect numbers, and so when they think about the number 1, they think about like 1.00000000000, and it's just perfect number 1. In science, things aren't quite so perfect. Usually, when we're talking about things in science, we're talking about things that humans have measured, and the devices that they use, the measurement apparatuses, can be flawed, and human senses themselves can be flawed. So when you are physically reading a ruler, you have to concern yourself with flaws in the ruler and just mistakes that you would make. And so things in science tend to be approximate or unsure in some way. So based on this, whenever we write down a number in science, what we're doing is we're only writing down those digits which we can depend on, because we have to communicate to other scientists how confident we are in the numbers. Generally speaking, when we're using a measurement device, this is going to include every number that's recorded on the device plus one more number that we're going to be estimating, okay? And we say estimating here with confidence, meaning we're pretty sure that we're right about the way that we've estimated it. Thing about this, let's say that you took a ruler and you measured something and you found that it was 21.7 centimeters. That communicates something specific in science, which we'll talk about in just a second. To a mathematician, though, 21.7, 21.70, 21.700, those are all the same number. In science, you'll see here in just a second, they are not. So in science, 21.700 means that you know and you're confident in this measurement to the thousandth of a centimeter. All right, you wouldn't have written down the 2 zeros at the end if you weren't confident to that point. You would have written 21.7. All right, so whenever we're writing numbers in science, be thinking about that. Be thinking about what you've written and how it communicates your level of confidence about a measurement that you've made. So generally speaking, in regard to this, if you're using a normal ruler, they're marked at millimeters, all right, which is 1/10 of a centimeter. And so what we say is with your eyes and with our brains, we have the ability to estimate a little bit past what we can see, and so, or what is visibly marked, I mean. And so what we can do is we estimate 1 decimal place past what's marked. And so if it's marked to the 0.1 centimeters, we can estimate to the 100th of a centimeter. So if you were sure that it was right on 21.7 and you had a ruler that was marked in millimeters, you would write 21.70 centimeters. So we're going to talk here about how we know what digits are important and which ones are not important. But it's important that you recognize that sometimes when we write numbers, specifically zeros, they're just placeholder numbers, and it's not that we actually know that it's a 0 there. It's mostly that we have to get the right decimal places established. So we'll put zeros there just as placeholders, and that'll make more sense in a second here when I'm talking about some examples of this. So there are 3 different kinds of zeros that we talk about. There are leading zeros, which are in front. All right, you can see here. Everything in the front of a number, if it's on the left-hand side, that's a leading 0. Trailing zeros come at the end, and then sandwich zeros are in between 2 other non-zero numbers. Of these zeros, the types that are placeholders, these ones are not significant, are leading zeros. Any zeros that are ever up front, okay, those are just placeholders and they're not significant. And also trailing zeros if there's not a decimal point. All right, those are just placeholders and they're not significant. So keeping in mind those two cases where we have zeros that are not significant will help you in the process of understanding what we mean when we write down numbers scientifically. As a note here also, if we're using scientific notation, ignore that times 10 to the whatever power that comes at the end, because that's just telling you how many places to move over the decimal place. And so that times 10 to the power, that is not part of counting sig figs. That just tells you about where the decimal place goes in your number. So you'll ignore that when you're counting significant figures. So now we'll go through and do some actual practice with this, and I'll explain, and hopefully things will make a little bit more sense if you've been confused up till this point. So counting the significant figures here in this first number, you have to first identify what sorts of zeros are in there. 2,500. The two zeros here are trailing zeros. All right, they're at the end. And then, in order to decide if they're important or not, we have to look and see if there's a decimal point. There's no decimal point here. That means that these two zeros are just placeholder zeros and they're not significant. To tell you what this number 2,500 means, if we read this in a scientific document, 2,500 written as it is there means 2,500 plus or minus 100. All right, if we wanted to say that we knew it was exactly 2,500, we'd say 2,500 point, because that would indicate that those two zeros there at the end are significant. All right, without the decimal point there though, we only have two things here that count. These are trailing zeros without a decimal point, so they're insignificant. So the 2 and the 5 are significant digits, and that's all that we have. For the next one, 4506. All right, that zero in this case is a sandwich zero. Sandwich zeros are never placeholders. They're always significant. So 4506, that has 4 significant figures in it. This next one, 0.00034. These zeros, if you look at them, hopefully you'll identify that they are leading zeros. Leading zeros are always just placeholder zeros. It's getting us out to that 10,000th and 100,000th place. And so really, those will never be significant. So the only thing here that's significant is the 3 and the 4. All right, those leading zeros never significant. So we just have 2 significant figures on this one. Now, 450 point. This one has a trailing zero, but it also has a decimal point. All right, so that trailing zero matters. And I say, think about whenever you're trying to make a point and you make it emphatically. And so a lot of times when you're, say, yelling at someone, you'll add the word period to the end of your sentence to make it know that you're serious about it. Like, I'm not ever going to do that, period. You know, I think that that's a good way of remembering what it means in this case too. If you say 450 point, you're saying you really know that it's 450. It's not 451, it's not 449, it's 450, period. All right? And so, in this case, we know it to the ones place. If it said 450 without the period, what we're saying there is we know it to the tens place, 450 plus or minus 10. But 450 points means that we know it exactly to the ones place, which means all 3 of these are significant figures. Trailing zeros with a decimal point count as a significant figure, so that's what we have there. In this last one, there are 2 different kinds of zeros. First, we have the leading zeros. Those never count. Now we have the trailing zeros, and you can see there's a decimal point in this number. So these trailing zeros count here as well. We wouldn't have written the zeros at the end if we didn't know them for sure. So that means we've got these 2 that don't count and these 2 zeros that do, which means that we have a total of 4 significant figures if you count the 2 and the 5. In addition to counting numbers that are significant or numbers that matter and are not just placeholders in a number, we also have to be careful when we're undergoing mathematical operations. So, generally speaking, what we have to do is we have to be honest about what we're communicating with other people, about how confident we are. And so I give an example in class. I ask people how many students there are going to our school. And usually they say something like this. There are 2,200 students, and I say, okay, how confident are you? Like if you had to bet your grade on it, plus or minus how many, would you be confident in? And most people are pretty confident within 100 students or so. So they say, all right, 2,200 students plus or minus 100 students. Okay, which seems pretty reasonable, knowing within 100 students how many students go to your school. Then I tell them, okay, let's say that we know that Marion High School is about 1/3 of the size, all right? And I ask you how many students go there. Well, for those of you who are pretty good at math, you say, all right, well, if we're going for 1/3 of the students, we're simply going to divide by 3. If we take 2,200 and we divide it by 3, we get 733 students, all right? Now we enter into a little bit of a problem here, because what we said about West High was that it had 2,200 students plus or minus 100 students. We weren't very confident in that number, 2,200. It could have been 2,300, it could have been 2,100, we don't know. All right, but then we go to talking about Marion High School, which is this other high school, and based on what we had said at West High, and it being 1/3 the size, we come up with 733 students. That seems like it's a bit problematic, because how can we know down to the specific student how many people go to Marion High School when we didn't even know how many students went to West High within 100? All right, so given some rules of Sig Figs, which I'll talk about here in just a second, it makes a little bit more sense to say that there are 730 students at Marion plus or minus 30. Okay, this demonstrates a similar level of confidence to what we had when we talked about West High School. So here's how the rules go. There are 2 different rules, and you have to keep them straight. The first one comes in when we're talking about addition and subtraction. The way this one works is you look at the decimal places, okay? And when I'm talking decimal places, I'm talking like thousands, hundreds, tens, ones, tenths, hundredths, thousandths. Look at what the most precise decimal place is, and that's what we're going to round it to, okay? Well, the least precise, actually, out of all of the different numbers here. So if we look at this first example here, we've got 3.535. That goes out to the thousandths place. All right, then we add it to 2.40. That goes out to the hundredths place. If we're adding these two numbers together, and we're trying to be honest about how confident we are, we don't know what comes after this 2.40 here to the thousandths place because it wasn't written down. So we're not very confident about the thousandths place when we add these together. So if you put this into your calculator, you get something like 5.935. But we have to round it to the hundredths place because that's the level of confidence that we have. So we round it to 5.94. So to sum up what we did there, we said we know this one to the thousandths place, we know this one to the hundredths place, so our answer should only go to the hundredths place. Going on to the next one here, we're doing another addition problem here. We've got 0.125, we're adding it to 4.1. This one we know it to the thousandths place, this one we know it to the tenths place, so our answer needs to be rounded to the tenths place. You add it together, you get 4.225. Alright, but we're going to round that to 4.2 because it needs to only go out to the tenths place. As a last example here, and this one will seem really weird, but we take 9 and we add it to 0.25. 9 is known out to the ones place. 0.25 is known out to the hundredths place. We go with the least precise. We're going to have our answer rounded to the nearest one. If you added them in your calculator, you get 9.25. But rounding to the nearest one, we just get 9 out of that. Now, from a mathematical standpoint, looking at that, it seems like complete nonsense. But here's why it makes sense. The 9 was so imprecise that, we had a pretty low level of confidence on this number. We didn't know that it was 9.0. We knew it was 9 plus or minus 1. So maybe 10, maybe 8, okay, somewhere in that neighborhood. Now we're adding 0.25 to it. This 0.25 is really precise, okay? But we're adding something really small to the 9, which we didn't know exactly what it was. It was plus or minus 1. Compared to that plus or minus 1, this 0.25 doesn't matter very much. Okay, so we end up with 9 again in the end. And this is just about maintaining an honest level of confidence when we're communicating our number. So that truthfully is how it works out when we're doing math and chemistry. The multiplication division rule is a little bit different. What we're doing with this one, instead of counting decimal places, we're counting sig figs. Remember when you're counting sig figs, you don't count leading zeros or trailing zeros when there's no decimal point. All right, so this first one, 10.0, those are trailing zeros, so there is a decimal point and they do count, so 10.0 has 3 sig figs. 2.5 has 2 sig figs, all right, so 3 sig figs divided by 2 sig figs, we're going to go with the smaller number there, we should have 2 sig figs in our answer. Now if you put this in your calculator, 10 divided by 2.5, you get 4. The problem with 4 is that 4 only has 1 sig fig, and we should have 2 to indicate our level of confidence. So to make it have 2 sig figs, we write 4.0. In this next example, we've got 0.025, 0.025. These zeros here are leading zeros, which means they don't count. So this first number has 2 sig figs. 3 is just 1 sig fig. All right, so we multiply these together. In your calculator, you get 0.075. All right, but we need to round it so that it only has 1 sig fig, since 3 only had 1 sig fig. And so 0.075 rounded to 1 sig fig is 0.08. And then this last example, this is going to be another strange one. 3 has 1 sig fig, 5 has 1 sig fig. We multiply them together, we get 15. But 15 would have 2 sig figs, and we need to round it to a number that only has 1. All right, so 15 rounded to 1 sig fig rounds up to 20. Now, again, this looks like something that would be really, really horrible and nonsense if it was in your math class. But in chemistry, it makes sense, and I'll tell you why. 3 here is a really, really imprecise number. All right, we're not very confident when we say 3. When we say 3 here, we're saying 3 plus or minus 1, so maybe 2, maybe 4, all right, somewhere in the neighborhood of 3. And we're multiplying it by 5 here, and again, we're saying plus or minus 1. So maybe 6, maybe 4, I don't know, all right? So we're not very confident in these numbers. And so when we multiply them together, we need to give you something that's in the right range, but something else that demonstrates that we're not very confident either. So 20 only has 1 sig fig, all right? This is saying 20 plus or minus 10, all right? So 1 sig fig there, it's a similar level of imprecision to what we had when we started off. So again, it's going to seem sort of weird to you, but try and get your head wrapped around the way that the math works on these problems. Going on to the next step here, it says sometimes you want to indicate that there's some trailing zeros that are significant, but others then aren't. And I'm going to give you an example here. So we're going to use an overline or an overbar to indicate this. So let's say we have 2,500 here, and we want to indicate that we know it to the tens place, but that we're unsure about the ones. So what we do is we put an overbar over it to say, all right, we know the tens place is a 0, but we don't know what that ones place is. All right, similarly, this next example, 190,000 known to the thousands place. So what we're saying here is we're confident in that first 0, all right? We're confident that it's 190,000, but anything in the hundreds or tens or ones is unknown, all right? And then as a last example here, 250,000 known to the hundreds place. So what we're saying here is we're confident that this first one is a 0, and we're confident that this one is a 0 here, but we don't really know what's going on in the tens or the ones place, all right? So if we counted these, the first one would have 3 sig figs, all right, the 2, the 5, and this first 0. This one here, this next one has 3 sig figs, the 1, the 9, and this first 0. And then this last one here would have 4 sig figs, the 2, the 5, and these 2 zeros. So anytime, and I'll give you some examples in class of when this would come up, but anytime you want to indicate a number of sig figs so that just some of the zeros are known that are trailing zeros and others aren't, we're going to use that little overbar to indicate that. Okay, I've said that sig figs are something that are pretty confusing, and they're also something that are a really big deal in chemistry. So if after watching this video and going through the practice sheet of problems, you're still confused on sig figs, make sure you schedule a time to come in and see me, because it's really crucially important that you understand this concept.